Hello community, so great that you are back. Today we have a new LLM by Carnegie Mellon University and the latest development from our policy optimization into a brand new policy optimization methodology. Now talking about this, you remember good old times here from OpenAI, the proximal policy optimization or PPO. You remember we can go two ways. Either we go here with the new value calibrated PPO, or we go with a group relative PO from DeepSeek. Let's have a look here. Let's open up and have a look here at the first one. This was here by ByteDance, March 3rd, 2025, and they analyzed, hey, what's behind the PPO collapse, especially if we go for a long chain of sorts. And they really analyzed this in detail and they told us, hey, we have two key problems with PPO in the long chain of sort tasks. And the real short, it didn't really become apparent, but now going here to reasoning models, we see that PPO collapses. Why? They develop here, or they investigated here, two biases, the pre-training value bias here and the in-training value bias. And for both of this, they found solution. Now, as you see here, the failure modes of PPO observed in the experiments, this is beautiful. And then they said, for the first one, we want to stick with a value model. So therefore, we introduce here a value pre-training. So this approach involves the offline training the value model until a convergence under a pre-specified fixed policy. And once the model has converged, it will be employed here in all subsequent formal experiments. And I've written down here the steps for you. If you are into this is a real technical challenging part, but I understand that they are tackling here the top two problems with PPO for long chain of sorts. Yeah, we have done a new policy gradient for an arbitrary delta, can be rewritten in a form, and you can code this, and you have kind of a value optimized PPO structure. But you know what? We have a second option. And from DeepSeek R1, this beautiful group relative policy optimization. Now, you remember this paper here by DeepSeek and Tsinghua University and Peking University is a year and a month old, February 5th, 2024. And they give us here the detail and the explanation here for GRPO. Now, the core motivation they tell us here, DeepSeek tell us here, is the inefficiencies of PPO's value function. And they say, the standard PPO relies on the actor critique architecture. The critique here is a value function model, often compared here in the size to the actor, the policy model itself. But training this additional value model, hey, this takes a long time. This is really computationally intensive. It incurs a significant memory burden and so on. And they said the value function training challenges itself because the rewards are often sparse and delayed, typically assigned only at the end of a generated sequence for a correct answer, and this can complicate the training of the value function in a real complicated way. And so they say, you know what? Let's forgo here the critique model. This means the value function entirely. So no value function in this simplification here of GRPO. Why is this possible that we can go here with a group score methodology? Now, the explanation is rather simple. Remember that GRPO, it reduces here the memory footprint and the computational overhead compared to the standard PPO, and this makes here the reinforcement learning fine-tuning of LLM much more feasible because our GRPO's group relative advantage estimation aligns very well with the reward model itself that are often trained on comparison between the outputs. So it is not about absolute value, but we compare, is A better or is B better? So this means that the reward models are inherently comparative. And this, of course, is great because now we have, if you want, a group relative advantage estimation. And we go here from, let's say, the mean value of the group. So this is great. These two meet here perfectly. And GRPO leverages this by calculating here the advantages relative to the other outputs generated from the same input. And now DeepSeek tells us here, just so think about R1. Experiments demonstrate empirically that TRPO is efficient in enhancing now the mathematical reasoning abilities of DeepSeekMath models, leading to substantial improvement over instruction-tuned baselines. So this was beautiful. But what we are today interested in is the stability of the system. Because remember, we are now operating here on long chain of thought, and we do encounter a problem. The system is not stable anymore. This means with some prolonged reasoning chain of thoughts, suddenly the system just goes pure hallucination, goes in a loop, and it's gone. So therefore, if you are a little bit more into technical details, TRPO uses the eclipsed probability ratio to limit here the policy updates, therefore ensuring stability. And this is quite similar to the original PPO, so it is real close to PPO. Now, the advantage, calculated to be group relative, as described above, guides now the policy update. But if you remember my other videos, we were also talking here about a Kullback-Leibler divergent penalty, no? Now, TRPO also includes a direct Kullback-Leibler divergent penalty to further stabilize the training and to prevent some drastic policy changes. We're going to have a nice coherent transition function, no? Therefore, DeepSeek now notes that the TRPO regularizes here the Kullback-Leibler directly in the loss function rather than adding here a separate Kullback-Leibler penalty to the reward, also sometimes done in PPO. Okay, now I would like to just have a walk back to, this is here in 2017 when OpenAI published here their PPO. And you know, it was interesting to see that before, this is already version 5, we had from UC Berkeley the trust region policy optimization. And I learned preparing this video for you here that in this trust region policy optimization, TRPO, which was before PPO, Berkeley said here the Kullback-Leibler divergence here is here the primary mechanism for ensuring stability in 2017 or 2016. So TRPO aims now to maximize the improvements while staying within a trusted region. So you see, we have suddenly here this environment term again around the old policy. The trust region is defined here by a hard constraint on a Kullback-Leibler divergence between the new policy and the old policy. And the idea, again, identical, is to prevent the policy updates from being too large and destabilizing here the learning process. So the idea was already here before PPO emerged. Now, interesting now, what I learned is that the eclipsed surrogate objective in PPO is, and you're not going to believe this, a simplification of the trust concept that was already used before in TRPO. I had the impression that PPO was invented by OpenAI, and now it turns out this PPO is just a simplification of a development by Berkeley. So this now designed to be much easier to implement and computational cheaper than the complex constraint optimization of TRPO, while still achieving similar stability like TRPO, and the performance is also similar. So PPO is just a simplification of TRPO. The world is small. Another option now, and I'm really going into the details, is that we have a PPO with eclipsed surrogate and a Kullback-Leibler penalty. So some PPO variant, this really depends now on the model that you're working with, add a Kullback-Leibler divergence penalty as a secondary optional regularization term for potentially finer control over the stability. So you see, stability of the system is the main topic, and we even go here with a primary and a secondary stabilizing mechanism. Okay, great. Or if you want to have it simple, you know, there still exists Wikipedia, and they tell us here, hey, PPO was published in 2017. It's essentially just an approximation of TRPO. Does not require to compute something complex. The Kullback-Leibler divergent constraint was approximately by simply clipping here the policy gradient. And then going forward, 2018, PPO was now the default reinforcement learning algorithm as published by OpenAI. So you see, it is all built on the shoulder of Giant and TRPO from Berkeley. Really interesting to learn this. So we need now a spark. We need a spark of genius. And you know, today we look I hope you knew all of this already. The topic today is now to go from GRPO, from the group Relative Policy Optimization, to LCPO, the length-controlled policy optimization. And when I read that Carnegie Mellon developed this new algorithm, this new policy optimization, I thought, hey, wow, this is interesting. I have to have a look at the paper. And you know what? Carnegie Mellon also developed a new LLM called L1. I suppose for Mellon University, the L1, maybe. The question is, why? Why do we need a new one? Because DeepSeek works just great. And they give us here the lack of control over the length of the reasoning process. This means the length of the chain of thought. Again, and they say, while longer chain of thought often lead to better performance, current models generate them in an uncontrolled way, leading potentially to some inefficiencies and making it difficult to manage computational resources for inference. You remember our 01 or 03 model that takes, 3, 5, up to 15 minutes I've seen lately. Computational resources, yeah, but we go for these reasoning models because we want a better answer. And now there is something interesting. If you read the study, they say we compare with S1. And you remember in S1, and I did a video on S1, this was Stanford University, S for Stanford 1 reasoning model, LLM, where they said, hey, we are close to O1 and R1, and Stanford has the S1, and now Carnegie Mellon has the L1. What a coincidence. And they now say, hey, L1 is better than S1, no? Because we have now a different mechanism. S1 just had this budget forcing. So it's also kind of a limitation here on the amount of the reasoning tokens, but they say, yeah, ours is better. Great. If you have not seen my video on S1, this is rather easy. We have an open mathematical data set. Then they used here Gemini 2 thinking LLM to extract or build up the reasoning traces for this particular problem. Then they cleaned all these reasoning traces and had then a reduced set of 1K data sets. And on this 1K data set, they supervised fine-tune here the Q1 model. And what came out was the Stanford S1 model. And now we have Carnegie Mellon University, the L1 model. So let's see what's the difference between Stanford and Carnegie Mellon. What changed in the technology? What is the core new idea? Length control. And this is it. You just want to control the length of your long chain of thoughts. So it's a simple reinforcement learning based method that gives you the reasoning language model precise and adaptive length control. And they do this in a very interesting optimization methodology. And they have two objectives, the correctness of the output and the generating reasoning sequences that meet here specific length constraint. If I say, hey, I want that my L1 model only uses about 8,000 thinking tokens or whatever, you can now kind of adjust the maximum amount of the length that you want to have this happening. Although I have to say, if I have a real complex problem, I don't know beforehand how many tokens I should give to the model. I don't think that this is a constraint if you have to pay for each thinking token. And yes, of course, you do have to pay for each thinking token. Yeah, so they wanted to make sure they build in a length constraint. Great. And they built two models, or they have two ideas, and then they built two models. So the first one was the LCPO exact, which requires the generated reasoning to be exactly equal to the user-defined target length. 3,847 tokens. And then a max version, which requires the output to be not longer than the target length. Now what they used. Remember I told you Q1 was here for Stanford here, the base model, and they tell us here, we fine-tuned here a very particular 1.5 billion parameter reasoning model, a real tiny model, I would say, no? And this is based on here on the Q1 distilled R1 model. So now that R1 is available really here, Carnegie Mellon says, hey, let's go with R1. Let's go with the down distilled version from R1 to 1.5B from Cuban, and this is a very specific model. I will tell you more about this in 2 minutes' time. So, having here two specific LCPOs, they build now the exact and the max L1 model. And as you see here on the very first page of the publication, they give us here, compared to Stanford University S1, Carnegie Mellon University L1 is better. Okay, so two friends, in a nice, friendly fight, in a nice, friendly competition. I said, hey, look, we are better than Stanford. Great. Let's have now a look at the publication and the fact. This is the publication, Carnegie Mellon University, March 6, 2025, L1 controlling how long a reasoning model thinks with really the latest reinforcement learning. And I was now interested, what is the advantage over our group relative policy optimization? Yeah, I thought Carnegie Mellon, extreme intelligent people, PhDs, what they did. Interestingly, they had their optimization problem here focused, as I told you, on two simultaneous objectives. The first one was the correctness of the answer, and the second was, because this is their selling argument, we can adjust the length, the reasoning sequence, the length here. Okay, so let's have a look. I was really interested to see that LCPO utilizes here the GRPO from DeepSeek. And I said, what? So they simply just used GRPO as the underlying reinforcement learning algorithm from DeepSeek? Okay, Carnegie Mellon. So R1, our DeepSeek, must really be outstanding in its performance, no? So let's have a look a little bit deeper. Let's go into technical details. Let's have a look at the notation they use for the L1 model, and it's rather simple. So they have an input prompt X and a specific target length, and gold, the golden standard, 3,845 tokens, generate now a response whose length n_y minimizes the particular form while producing the correct answer. So you see, again, we want to have it correct and define 2-hour length. How is it done? And now comes the rather simple approach, I would say. You just augment each prompt here with the instruction of the target length. So X is your prompt and you concatenate to X sync for exactly 3,000 tokens. And I thought, wait, this is the new advanced length controlled policy optimization in RL? And I had to look, no, can't be. So I looked at L1 exact, beautiful, and they define here the reward function, and the reward function has two terms, the correctness reward, you remember, objective 1, and the length penalty, objective 2, and it's a simple form, this is the indicator. So now we have alpha. Alpha, I think, is an interesting parameter because it gives us here exactly the equilibrium, no? A lower value of alpha now prioritizes here the correctness of the answer given by L1, whereas a higher value of alpha enforces here a stricter adherence here to the length constraint. Now, I'm not really happy with this idea that either I can go with the correct answer and I lose here the length control, or I have to have the perfect length control of my long chain of thought, but I have not really the correct answer. So going for this particular optimization problem, I thought, interesting. Then I looked at L1 max, and they just fine-tuned the L1 exact model using now here the same reinforcement learning framework, but now with a modified reward function. And you see it exactly. So here again, alpha now controls the penalty for length violation. And we have the same idea. So I said, interesting. Maybe I would have expected something new, some brand new ideas, some genius, but okay, we have a length controlling term in the reward function. This is it. And then I looked at the training process and said, maybe in the training process, there's something outstanding here by Carnegie Mellon. So more or less 3 points. Now we have a pre-trained model, like Stanford, we start with something. And LCPO starts with a pre-trained reasoning model, and in this case, this is now a very special model. I'll explain this model in a minute. Deep scale R 1.5 billion preview. This is now a model originally RL fine-tuned from the DeepSeek R1 distilled Q1 1.5b. So again, we are here with the R1 distilled R1 version. And then we fine-tune this with our reinforcement learning using a GRPO algorithm. So this is R1, this is from R1. And now the new reward function that have this particular term to control the correctness against the optimized length constraint. This is the new part here, this new reward function. Yeah, you train it and then you have an iterative optimization up to the model policy. And yeah, learning here to the correct answer within the desired length constraint. So you always have to balance, is it the correct answer or is it rather the correct length of the answer? So content versus form. And then I thought, so wait a minute. So this is now the new L1 model. And I thought, so what do we have? We have from DeepSeek R1 a distilled model. So R1. And this is fine-tuned now on the reasoning traces of the real DeepSeek R1 undistilled model. So this means the whole reasoning comes from the, let's call it intelligence, quotation mark, of R1, of DeepSeek R1. And then we take here the policy optimization methodology, the GRPO, from R1. Now, can you spot what I thought when I saw R1 from R1? And this is now L1. Okay. Just as a comparison, this was Stanford, yeah? With Gemini and QN 2.5. So let's come to the end of this video. Maybe a little bit surprised, no? So interestingly, yeah, they always reference here to Stanford S1 model, and here's the text compared to the Stanford S1 model. The only other method specifically designed here for a length control in the long chain of thoughts. L1 shows here remarkable improvements because they used the reasoning traces of R1 that was not available for S1, and they used here the policy optimization that was not available for S1 from R1. So L1 shows remarkable improvement, 150% relative and 25% absolute performance gains. Then they praise the model as explicitly trained and, effectively distilling reasoning patterns from longer chains to shorter ones. And I thought, yes, the reasoning pattern by R1 are really outstanding. Therefore, I guess this is why Carnegie Mellon used them for their L1 model. Let's look at the code. I thought maybe there's a beautiful code implementation. So here we go, Carnegie Mellon University L1, beautiful, 16 hours ago, already 16 stars, great, and here you have controlling here L1, beautiful, this is all here, and then they're absolutely beautiful, there's an acknowledgement, we would like to thank DeepSeek for releasing the R1 and the distilled model, and Q1 for the Q1 math models, beautiful, and Agentica for code base, and I said, who is Agentica? What do you mean for code base and open sourcing their models and their data sets? And I thought this was done by Carnegie Mellon. So beautiful that they also reference this, absolutely great. And I have here a citation, everything is beautiful. And I said, who is Agentica? And this is now the interesting part that I learned. Maybe you know it and great, but it was new for me. So part of Berkeley's AI research and the Sky Computing Lab here from Berkeley, this is here a Agentica project, and they have on GitHub their repos, beautiful. And if you look a little bit closer, those are the people from Agentica. And they have an open source initiative, and they want to democratize reinforcement learning techniques for everybody, so that everybody is able to use their code open source and develop scalable systems for LLM and agents. And they provide you the models, they are code-free, open source. So they have here this project DeepScale R. So, and the idea is surpassing here the OpenAI O1 preview with a 1.5 billion model by scaling reinforcement learning. You remember, just 2 videos ago, I was talking to you about scaling reinforcement learning. And they make now the same on a 1.5 billion. I was talking about a 3 billion. Now we are down to a 1.5 billion model to surpass O1 preview. So, core contribution, those are the authors. And I say, hey, thank you guys, great work. Never heard of you before, but I really do appreciate. This is from February 10. Wow. And then you look here at their DeepScale repo from last month. Beautiful, close to 2,000 stars. And you'll see real nice. They have everything there. They have an MIT license on their model, on their code, on the data set, on the training code. So if you are not familiar, I think this is a beautiful source. And just looking at them, they say here, DeepScale R is an open source project to fully democratize reinforcement learning and to reproduce DeepSeek R1 and OpenAI O3 at scale for real tasks. If you really can, if you want, reproduce here an open source O3, this would be really interesting. Yeah, and for all releases, we open source all of our efforts here, including the training scope, the hyperparameters, the model, the dataset, and the logs, and it's all MIT license. Beautiful. And then I discovered that this specific here model that Carnegie Mellon used, this DeepScale R 1.5b, this is the model from them, from Agentica. And is that absolutely fascinating. The world is a small place. So maybe you knew it, maybe not. They give you exact instruction how to install the code, how to run this, the training recipes, the inside. So if you are interested to build here the code base for scaling reinforcement learning with the latest idea, with the latest policy optimization, I think this is an excellent source of code. So coming back to Carnegie Mellon University, there was something I would like to address at the end of this video. They mention here the different reasoning strategies of their model L1. And they have here the sentence, L1 employs distinct reasoning strategies at different token budgets. And they say, hey, this is kind of the speciality of L1. So different token budget, I get it. If you have here, let's say, 500 tokens or 4,000 tokens, okay, great. But to claim now that the reasoning strategies are different, if you have 500 tokens or 4,000 tokens, I thought I have to have a closer look. So how is this possible? And their idea that this is a valid sentence comes from this graph here. And they say, you know, when we looked for the words therefore and for the words so, those two words here, when we have given here the reasoning LLM 4K tokens to reason, we found that the word therefore was so much more used than before with only a 500 token answer. So therefore, this conclusion drawing, so these strategies, they are now distinct reasoning strategies because the word therefore and so are now used more. I personally do have a problem that those are distinct reasoning strategies if you just count the word therefore and so. So maybe I'm wrong, maybe this is the way to go, and Carnegie Mellon, absolutely beautiful, intelligent people, but claiming that L1 employs here distinct reasoning strategy. A strategy for me is a much more complex object. No? Counting here the word therefore, if you have here a long chain of thought reasoning. Okay, so yeah, maybe you have your own opinion about this particular thing. This is the end, and I would like to maybe redraw my thumbnail for this video. You know, having now in detail looked what is here this length-controlled policy optimization, you know, it is the group relative policy optimization by DeepSeek R1. They have an additional reward term to control the length, and they have a relative length control and an absolute length control. Okay, but I think if we look just at the technological advancement, this is almost identical. So I would say, I would modify this thumbnail part here, and then if I say the new L1 model, maybe I would say parenthesis from or 1 from DeepSeek or 1, then I think this is the perfect thumbnail for this video. If you agree with me, why not subscribe to this channel? Because the new video is already coming up tomorrow.